It's a pleasure to be here today, and I loved having Christina in the lab. We miss her, and she will make an appearance in the talk, actually. I was so honored when Darnell contacted me and invited me to come and speak here. I have a very high opinion of the University of Chicago, and one of my colleagues in economics, actually, Chloe Gibbs, speaks very highly of her experience in this program, actually. I think 10 years ago, she was doing what Darnell does as the coordinator of the workshop, and so I'm so excited to be here today and share some of my work. As Christina said, I'm an experimental psychologist, and my work is at the intersection of cognitive development and mathematics education, and my primary interest is in the development of mathematical cognition. So basically, I study how children come to develop an understanding of math concepts. And today I'm going to present some research that my colleagues and I have conducted that shows how small changes...
Just let you know that window is...
Oh my, thank you for letting me know.
That's gone.
Okay, so yes, I'm going to present some research that my colleagues and I have done over many years that suggests that small changes in the structure and format of the things that we present to children can affect their understanding of foundational math concepts. And of course, researchers in psychology and other social scientists have a history of showing how holistic differences in children's environments, such as socioeconomic status or family structure, or the amount of television viewing or the quality of the early child care environment, affect cognitive and academic outcomes. But more recently, we've started to recognize that even differences in more localized, fine-grained aspects of the environment can affect children's understanding of important math concepts. Now, from my perspective, there are at least two really good reasons to care about the development of mathematical cognition. You might think that's a very narrow and specific domain to be studying, but first of all, there are interesting theoretical issues. Mathematics is a remarkable human accomplishment, and of course, we evolved some of the capacities that support mathematical thinking, but we also invented many of them, like the symbolic notation that we use to communicate mathematical ideas. So by studying the development of mathematical thinking, that provides us with a window onto the nature of human knowledge. And we can ask deep questions like, what do young children understand about math before they start learning it in school? And how does math understanding change as the result of language or culture and education? Additionally, because math problems are well-defined problems, they are excellent tools for testing questions about mechanisms of learning and cognitive development. And if you're familiar with Susan Golden Meadows' work, you will be interested in this use of mathematical problems. So we can ask questions like, where do new strategies come from? And how can the transition period between one knowledge state and another be defined? Now, these theoretical questions would be enough for me to keep studying the development of math cognition, but fortunately for everybody else, there's also practical reasons to care about the development of math cognition. So, first of all, early math skills are one of the strongest predictors of future academic achievement, even more so than early reading skills, attention skills, or socio-emotional behaviors. And later math skills are also important. So understanding of algebra in particular has been identified as a gatekeeper to future educational and employment opportunities. Basically, if you don't do well in algebra, you're going to be severely limited in terms of your educational opportunities. And as Robert Moses has said, it's not only a barrier to college entrance, but it's a barrier to citizenship. Math skills are important to society as a whole. As you've probably heard many times, students in the U.S. consistently lag behind their peers from other industrialized nations in terms of their math understanding, and this is a concern for our competitiveness in the global economy. A report several years ago out of Harvard suggested that our students' poor understanding of math could cost our country $75 trillion over the next 80 years. Now, I'm not an economist. I don't know about the validity or if that report was well-founded, but it's out there. So from a practical stance, it's important to understand more about the development of mathematical thinking, so we can help parents and educators provide children with the tools that they need to succeed. Now, the assumption, of course, is that the environment matters. I know that many of you in this room are familiar with some of the research out there on the broad, sort of holistic aspects of children's environment that affect cognitive development and academic achievement. Things like daycare or family structure, television viewing, use of technology, and poverty. And of course, poverty justifiably receives a lot of attention. So, for example, you might know that there are differences in general academic achievement between school-age children growing up in poverty and school children growing up in more advantaged homes. That's illustrated in this graph with reading achievement. And some researchers out there in psychology have suggested that these differences in achievement may begin before formal schooling, and they may be rooted in children's early language differences. You may have heard a report that by the age of 3, children in middle versus low income homes hear about 30 million words difference. So children in middle income homes hear about 30 million words more. Now, whether these differences are conceptualized as gaps or deficits, or whether they're just sort of two different ways of being in the world, that one has an advantage, that's not the purpose of this talk. We could have a discussion about that. But my point here is that a lot of people have heard about early language differences. A lot fewer people have heard about early math differences. So before children start formal schooling in kindergarten, there is already a large gap. Now, people in this room might be more familiar with that than, say, out in the general population because of Susan Levine's work here, because she's a leader in this area. But if you ask this sort of everyday parent, they may have heard about the language finding, but they don't really think about early math skills as being very different. Okay, so now, the focus in this talk isn't going to be about poverty. It isn't going to be about big differences in children's environment. What I'm going to try to show you with 3 sort of small examples is that even fine-grained differences in what children see in their input have implications for the knowledge that they construct about math concepts. So what I'm going to do is to make this, to go through this talk, I'm going to start with the preschool age, then I'll move up to school age, and then I'll move up to middle school, and I'll show you an example in each age group of a small, seemingly minor difference in children's environment that seems to have implications for the concepts that they construct. Okay, so we're going to start with a practical decision that teachers and parents of young children have to make. I want you to imagine that you're a preschool or a kindergarten teacher, and I want you to say that you want to plan some lessons on counting. You want children to understand number, you want them to learn how to count and understand why you count, what it means. What types of materials would you choose for your lessons? Would you want to choose physical objects, or would you want to choose picture books? Let's have a show of hands. Who wants to choose physical objects? Okay. And how about picture books? Okay. Somebody who picked physical objects, are you willing to share why you're choosing physical objects? Why might you want to use physical objects for your lessons?
You can manipulate them.
You can manipulate them. Okay.
You can touch them, and maybe what you hope touch affects how you.
It provides a tactile representation of the concept, potentially. Did anybody have another idea?
They're utilizing more than just their visual sense to comprehend it. They're able to manipulate it, and depending on the kind of learner, that is probably important.
Okay. Other ideas?
And they're individual things, like they would help with individuation and like mapping what counting is, and 1 thing, 2 things, 3 things.
Yeah, so if the major thing that you want to get across is the individuation of the items being counted, they might help with that. Did we miss anything that somebody who chose physical objects?
They might provide you with more feedback. Going off of the manipulation thing, you can manipulate it and see one way and then manipulate it and see it in a different setting, but you can't really do that with pictures.
Yeah, and you kind of can control your environment more. You're constructing your concepts a little bit more when you have the objects. Okay, now somebody who chose pictures. Tell me about why you chose pictures. I saw hands.
It requires more abstraction, so you have to be a little bit more sort of broad and thinking about what you're talking about.
Okay, pictures require more abstraction. Yeah.
Less distraction, like you can't sort of do other things with it.
Yeah, so it's harder to play with pictures, for example. You can kind of play with physical objects, and that might be distracting. Well, these are touching on reasons out there in the literature that there were sort of conflicting views about whether physical objects or pictures might be better for helping children understand counting concepts. First of all, when we surveyed teachers, all of the preschool teachers thought physical objects would be better. They said, if I'm going to do a lesson, I want to use the physical objects. They cited things as being more engaging, more motivating. Children would want to come and work with the teacher. We heard more manipulatable. Another thing, this is related to gesture work, is that pointing and touching can help you keep track of counting, so that may be a benefit of the objects.
Yeah, but pictures elicit gesture too, so.
That's true. Yes, that's true. Yeah. In terms of the pictures, as Lindsay said, they're a little bit more abstract. And here's a concept that I want to introduce. It's pictures have greater representational status. That means they're better representations of other things. So they're less distracting, is what Susan said. They have a clearer teaching purpose. You know, when you see a picture, it's communicating about something else. It's not as interesting as an object itself. There's some research to suggest that helps children focus on the set as a whole. It goes back to, do we want kids to be focusing on the set as a whole, or do we want kids to be individuating? And both are going to be important. It depends what you want to teach them. The thing that I care about a lot is children's understanding of the cardinality principle. So I want to take a moment and do an aside to make sure that everybody understands what the cardinality principle is. Okay, so of course many children, like even 2-year-olds, can learn to count from 1 to 10. I'm not going to present this video just for time so I can get through everything, but this is a child a little before 2 counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A lot of parents think that's what, once you know how to count, that's all they need to know about counting. It takes children many more months to understand like what it means and why they're doing it. After several months, they may even be able to do sort of the one-to-one correspondence, 1, 2, 3, but it still takes longer for them to truly understand what it means. And I think that this video provides a nice example of that. So let me show you this.
This one's the first one we're going to do. So
Christina! But he was pretty good up to 15. You might think, okay, he's got 15.
you can monkey 1 orange. Is that 1? Thanks. You can throw that one. Okay. Yes. You can monkey 2 bananas. Is that 2? Yes. Thanks. Okay. You want some strawberries? So you can monkey 3 strawberries. Is that 3? Yes. Thanks.
Okay, so clearly not up to 15. And interestingly, it seems to be the case that children go through the same developmental progression toward their understanding of the cardinality principle. So first, they become what's called 1 knowers, which means they can give you exactly 1 if you ask for it. Anything more, they fail. After several more months of development, they become 2 knowers. They can give you exactly 1, exactly 2, anything more, they fail. Then they become 3 knowers after several more months of development. Then after several more months of development, maybe they're 4 knowers, maybe they're not. We're not going to get into that. But right around the point at which they understand 4, soon after that, it seems to be the case that there's a quick qualitative difference in what they can do, and they can give you any number in their count list. And that is when they are called cardinality principle knowers. So this is actually the last counting principle to develop, but you might say, like, who cares? You know, all adults understand cardinality. Why, you know, they're going to get it. It's not like, you know, people are going around not knowing what 5 is. That's true, but the age at which children understand cardinality varies widely, as Susan Levine and her colleagues' work shows, right? Some 3-year-olds are already cardinality principle knowers, but when some 5-year-olds getting ready to start kindergarten are still only 1 knowers. So that means that before they start kindergarten, there's already a huge gap in what children understand about early math concepts. And it's not like the gap goes away once they start school. Early differences keep growing as children progress through their mathematics education in school. So, and in fact, Christy Van Marl and David Gary in a recent paper at the beginning of this year in Psych Science showed the age at which children develop understanding of the cardinality principle predicts their math understanding in 1st grade. It's one of the better predictors of children's understanding of math in 1st grade. So these early individual differences do seem to matter. Now, given the foundational role of cardinality in children's future achievement, you might say, why isn't there more work on this? Well, slowly people are starting to do this. We obviously assume that the environment matters. There's a variety of different now preschool math curricula out there, and cardinality is the focus of in all of the math curricula that are out there in standards. And as if you're familiar with Susan Levine's work, there's empirical evidence suggesting that the way that parents talk with their children, the quantity and quality of their math talk when they're, say, 2-year-old will predict their understanding of cardinality at 4 years old, for example. So we know that the environment does matter for children's understanding of cardinality. But the question is, what kinds of things? So math talk, yes. What else? What are the malleable factors, right? We're coming from an IES perspective here, right? IES wants to know about the malleable factors that affect learning of cardinality. So when we see a 5-year-old, when we go to a Head Start, one of our local Head Starts, and we see a 5-year-old that is still only a 1 knower, what can we do to speed up that development a little bit more so they're in a better situation when they get to kindergarten? Because what they learn about arithmetic in kindergarten is based on understanding of cardinality. You need to understand it to compare numbers, to add numbers, to subtract numbers. So what kinds of things are going to affect that? Now that gets us back to the question of objects versus pictures. So this study was the first study that we did in this series of studies looking at what might be malleable factors in children's environment. And in fact, it was conducted by one of my previous graduate students who then worked with Susan Levine. Her name was Lori Peterson, and she is now a professor at Purdue Northwest, and this was her dissertation. So Lori wanted to know, does children's understanding of cardinality benefit more when they use physical objects or when they use pictures? So in her study, she randomly assigned children, preschool children who were 3 years old, either to learn with physical objects or with counting books. And they were randomly assigned to practice one-on-one 5 weekly sessions with an experimenter, and there was a pre-test of their understanding of cardinality and a post-test of their understanding of cardinality. Just to give you a sense of what this looked like, here's an example of the picture condition. It's just binders. We've improved dramatically since this initial study, but this is what the counting books looked like. It was just pictures of objects in a binder. The object condition was the same in all ways, except it was the real physical objects. both before and after the intervention, we assessed children's understanding of cardinality, and we did that with the give-n task, which is the video basically that you saw. And children are given credit for being a knower of the number of objects they can give reliably, and all lower numbers. So 1 knower, 2 knower, 3 knower, 4 knower, cardinality principle knower. Okay, and again, we want to know, is it better to count with objects or is it better to count with picture books? Here's what Lori found. So on the y-axis here is the average knower level, and this is the objects condition, this is the picture condition, and it isn't a huge effect. The sample size was very small. Lori is still currently conducting a replication study. She doesn't have as much time for research now that she's at a teaching heavy institution, but she is working on a follow-up to see if we can replicate this. But what she found in her initial study was that the objects were more likely to propel children's understanding of cardinality. I mean, the pictures were more likely to propel children's understanding of cardinality than the physical objects. So, at least from the pilot study, it looks like pictures are the way to go. At least if you want to focus on children's understanding of cardinality. The project that we're doing currently is related to this. So if you go out there in the real world, so our materials were not very real world, but if you go out there in the real world and you find counting books, you will notice that counting books differ according to how physical the objects are in the books. Now, is the tactile, physical, pasted objects on a page, is that similar to physical objects in space? That's what we're going to find out. So in this current study, it's a large study. We're working with 300 children, and we're randomly assigning them to a tactile counting book or a regular 2-dimensional counting book. And I don't have results to show you, but just to give you a sense, this is the current study that we're working on. Okay, now I'm going to move up the age to elementary school. And I'm going to say, I want you now to imagine that you're an elementary school teacher, let's say 2nd grade teacher, and you would like your students to practice their arithmetic facts so that they can be fluent and they can have conceptual understanding of arithmetic, all that sort of basic understanding that they need to be able to succeed in higher level math. Which way would you have your students practice their math facts? Would you have them practice like option A, or would you have them practice like option B? How are you going to get your students fluent with their basic math facts? How many people are going to choose option A? Okay, and how many people choose option B? Okay, tell us why you chose option A.
Well, maybe I was wrong. I mean, it's just more consistent with how I think and how I think I was taught, and how, like, it's consistent with like how I think we're taught to, read at an early age to just going from left to right. Maybe our reason goes that direction too.
Excellent. Okay, now somebody who chose this one, why did you choose that? A lot of hands were up. Yep.
We can support the idea of being able to think about these things flexibly and understand the relations between these numbers more than thinking that it has to be in a certain order for these numbers to relate to each other in that way.
Okay, great. That is reflected in the literature. Usually in a room, I get about half and half. This was unusual that a lot of people were, almost everybody was choosing option B. But sometimes people think option A, the sort of I'll call the traditional format. Teachers and textbooks, that's what they use. That's how we were taught. But also in cognitive psychology, we know that invariant structure speeds learning. So you may become fluent faster if you have invariant structure. And maybe if you're with 2nd grade children, that, switching the format all around, that might just be too confusing. You might have to start with the that's an opinion out there. But the traditional format may lead to problems then when children get to higher level math, right? And especially when they get to algebra, because that traditional format doesn't highlight the interchangeable nature of the two sides of an equation. And so it may not be good for producing or getting children to develop a good conceptual understanding of the relational nature of equations. And that's what they're going to need when they get to algebra. So we have a series of experiments that we've done related to this issue. These were funded by IES, and these experiments are with second and third graders. The basic procedure is that children come in, they practice basic arithmetic facts with one-on-one with a tutor, and then they complete assessments to assess their fluency with basic math facts and their understanding, their conceptual understanding of the relational nature of equations. And children are usually randomly assigned to different conditions. In one study, we studied that example that I had to show you, right? Do children practice 3 plus 4 equals blank, or do they practice blank equals 3 plus 4? Just to give you a sense, they do flashcards, but they also play games. It's about 100 minutes of practice over the course of the intervention. Here's one of our games. It's a slammer game. They get a little hand that has a suction cup, and at each turn a number is flipped over, and the tutor and the child race to smack the problem where that number should go in the blank. And so this is the traditional format of the game, and this is the non-traditional format of the game. You can see that they're similar except the problem format. Children are practicing the same problems across both conditions. The computational fluency measures that we use post-test are the computation section of the Iowa Test of Basic Skills, and then we also give a sort of psychology, one problem at a time, and get their reaction time on single-digit addition facts. To assess their understanding of the relational nature of equations, we use math equivalence problems. If you're familiar with Susan Golden Meadows' work, then you maybe have been introduced to these before. But here's an example of a math equivalence problem. Children tend to solve these problems incorrectly. So let me show you an example of probably the most common strategy, certainly on this blank type.
Okay, can you tell me how you got 15? Okay.
She's a matcher. Same hand shape across all the numbers, though she doesn't quite go, but so this is one of our measures. It's an equation solving measure where they solve problems with operations on both sides of the equal sign. We also give an equation encoding measure. In this task, we show them a problem. We say, you don't have to solve this problem. I just want you to remember what you see and write it down. So they see a problem for 5 seconds. After it gets put down, they write exactly what they saw. And a number of children will write that they saw problems like this with the equal sign and answer blank at the end. And then we also ask them to define the equal sign. Here is a very common definition of the equal sign that the children will give.
So let's take a look at this math symbol. What is the name of this symbol?
An equal symbol.
What do you think this symbol means?
When you add something and add another thing and keep going on, when you stop adding, then it says that sign to see how much you've got.
Okay, that's a very common understanding of the equal sign in elementary school children, and even middle school children, about 50% still have this kind of operational understanding of the equal sign. So again, just to recap, what we do is we randomly assign kids to practice math facts in one of two conditions, and we assess their understanding of math equivalence, but also of their fluency with basic math facts. And so the first thing I'm going to do is show you a table. It might be a little overwhelming, but this is the fluency with math facts measures. And so we have accuracy when they're given a addition problem, 3 plus 4, 7 plus 9. That's at the top. The reaction time is the middle, and then the ITBS score is the bottom. And the main thing here is that there is only one thing that differs, and that's this, that the control kids take longer to solve the basic math facts than the other two conditions. We don't see any evidence of differences anywhere else. But what about conceptual understanding? That's what you'll see in this graph here. So on the y-axis here, I have a composite score for their solving of equations, encoding of equations, and defining of the equal sign. The results are similar across all those measures. So here we have a sum of the z-score as a composite measure. And this is the control condition. This group receives no practice more than what they typically get at home or at school. This group receives about 100 minutes of traditional arithmetic practice using our flashcards and games. And this condition receives the non-traditional, where it's blank equals 3 plus 4. And so you can see from the graph that the children in the non-traditional condition are more likely to develop a relational understanding of equations, an understanding of math equivalence after their practice. We've also found the same thing in the context of classrooms now. So you know IES, right? You want to start in the lab, you want to get bigger and bigger and bigger. So we started in the lab, then we moved toward a classroom intervention where we had children participating in arithmetic practice workbooks in their classrooms. So in this study, we had 166 second graders. Here, the basic procedure is that children within a classroom are randomly assigned to one of two types of arithmetic practice workbooks. One has the traditional format, one has the non-traditional format. And teachers use the workbook in class. Everything's handed over to the teachers. There's a suggested schedule. They do it like twice a week for about 12 weeks. And here's just some examples of how the traditional and non-traditional differ. The same problems are practiced across the workbooks. Here's one of the non-traditional pages. Here's one of the traditional pages. Here's another example, non-traditional, traditional. And so after children use these in their classroom, we come back and we assess the same things that we assessed before, their understanding of math equivalence and their basic fluency. And so here's what we find in terms of their understanding of math equivalence. Again, we have a composite on the y-axis. Here's their workbook condition, traditional, non-traditional, and we can see that it works in the classroom. When teachers are doing it, they're using it as part of their regular routine. They practice either with the non-traditional format or the traditional format, and that traditional format does improve their conceptual understanding of equations. And we don't see any difference, again, in their basic fluency. Okay, so which way would you have students practice? I'm going to say it seems to be a difference, and that I would recommend this way over this way. Yes?
I forgot, in the first one, I know the traditional one, they have faster reaction time, right? But was it not significant?
That's right. It wasn't. But you still raise a point. I believe that if we had a larger sample size potentially, or the practice went longer, I would be surprised if the traditional wouldn't get a little bit of an advantage in terms of reaction time for those specific basic facts that they practice. I would be surprised.
Because it seems to be one of their main contradictions in learning math, or complementarities, is automaticity.
Yes.
Basic stuff that you don't have to think about.
Yes.
You just know it.
That's right.
So that you can focus on harder things, problem solving, versus having the reasoning skills to set up the harder things. Yes. If you try to set up the harder things, you don't have automaticity. So I'm wondering whether there would be some blend of these things that would be better than just one or the other.
So what I'm advocating for is the blend. Mm-hmm. I personally feel I'm not somebody who says you shouldn't practice your basic facts. There are people who do say that. They say calculators can do that. We don't want to focus children's attention on doing these calculations. I personally think there is a benefit of facts practice. However, I would say when you practice your facts, move the format around. It's going to take you my guess would be a small amount of time longer before you gain automaticity, but you want what you ultimately gain automaticity with to map on to the important foundational concepts that you will need later on for when you learn algebra. So my personal opinion that I would recommend to parents who ask me is, yes, practice facts, but make sure you're doing it in a way that is reflective of the underlying structure that you want them to get. Now, I have had people in cognitive psychology push back and say, I actually think the operational view is okay. And what you really want to do is you want to get kids really proficient with that operational view and then really proficient with the relational view and get them to flip back and forth. Okay. So that is a view out there. However, we have work with undergraduate students. So these are students who had elementary school in the United States, but now are at University of Notre Dame, University of Wisconsin. I mean, these are good schools, right? They understand algebra. But by getting them to practice basic math facts in the traditional format, we can actually make them look like kids, where we'll give them a math equivalence problem with operations on both sides, present it for only 2 seconds, and then they will add up all the numbers. Now, the interesting thing is they're more likely to do it after practicing basic math facts, so that counters sort of the John Anderson skill acquisition, the subcomponent skills. If you get fluent at them, are going to automatically make you better, because actually the problems that we present in that study have the facts that they practice in them. So the facts that they practice, so for example, 3 + 4 + 5 = 3 + blank, they would practice 3 + 4. Do you see what I mean? Like the facts that they practice are actually contained in the problems that they have. But after practicing basic math facts, they are more likely to add up all the numbers than if they come in and just do nothing. Additionally, this is an interesting piece of data. If they had elementary school in a high-achieving East Asian country, they do not make the error. They do not add up all the numbers. And that it would be predicted, because if you, like, in the United States, about 80% of children will get these problems wrong, 2nd, 3rd grade. If you go to a high-achieving East Asian country, over 90%, let's say China, over 90% of Chinese first graders can solve the problems correctly. So they don't develop the operational misconception to begin with, and then it isn't there to activate when they're undergraduates. So
because of their language.
Well, there's a lot of things that differ, but there is better knowledge of the base 10 structure because of the language, but also there has been an analysis of the textbooks, and they do things that promote relational understanding. First of all, before they get to teaching arithmetic, they teach the equal sign outside of an arithmetic context, where they develop, like in the preschool kindergarten year, the idea of the equal sign as a relational symbol before they introduce it in arithmetic. And then in arithmetic, they do vary the format when they're drilling. So anyway, for that reason, that's why I would recommend this way. But it's still an empirical question, I think. Nobody's tested whether starting this way and just gaining fluency here is better or worse than teaching them to flexibly switch between the two.
Can I ask?
Yes.
Sorry, I'm sitting on the floor. I can't recall, does your outcome measure have addition and subtraction facts, or just addition facts?
The ITBS has addition and subtraction facts on it. The reaction time measure of the single digit is just addition. So the standardized test is both, but the reaction time, one at a time measure, is only addition facts. Yeah?
So it seems like the non-traditional format is not only like moving around the equal sign, it's like a mixture of additions and subtractions. So if like 6 is equal to blank plus 1, you're actually doing a subtraction of 6 minus 1. So
You can. That's not how children initially start solving the problem. But yes, you can solve the problem correctly by doing subtraction. The way that children do this when they very first start doing it is they go, what plus 1 is 6? And they'll go like 1, 2, 3, 4, 5, 6. It's 5. But you can do subtraction. They don't quite get the inverse relation between addition and subtraction that we do at this age. More questions? Because I'm going to switch to middle school. Yeah.
Did you like track whether kids were initially confused by it being in the non-traditional way and kind of asked, and whether the teacher or tutor explained that the equal sign means, has that relational meaning?
So did we specifically teach children that the equal sign has the relational meaning?
I just imagine that they might see it and be confused and say, what is this? And then the teacher or the tutor would then explain it.
So I didn't go through all of the... So we do flashcards as part of our intervention. And children in both conditions, the way that we have them do flashcards is first they have to read the problem. So if they get this problem, they have to say 2 plus 2 is equal to blank. They do that in the traditional format and in the non-traditional format. They have to say blank is equal to 2 plus 2. And the tutors do give them feedback on that. So like if the kid just gets this and says 4, the tutor stops them and says, remember, you have to read the problem first. So in our flashcard practice intervention, we have them, that's our way of sort of trying to get around that, right? It makes it very explicit what's happening. But we never say, now remember the equal sign. We don't give any sort of conceptual instruction beyond you have to read the problem before you tell us the solution. Oops, we can talk more about that too at the end. So now we're at the middle school level, and I want you to think about, pretend you're a middle school teacher, and you want to use a literal symbol to represent a variable, right? Let's imagine that you're representing the price of cakes and the price of brownies. Which literal symbol are you going to use? Would you prefer to use C for the price of cakes and B for the price of brownies? X for the price of cakes and Y for the price of brownies? Or something even, what is this, phi and psi?
Yeah.
Okay, how many people want to choose option A? Cake, C, and B, okay? And how about option B? Okay, and option C. Okay. Okay, so nobody choose. That's fine because actually these two are very similar. I'll spoil it. Spoiler, these two are similar. Okay, option A. Why do you want to choose option A? There were quite a few hands.
Because maybe children will have an easier time kind of keeping track of what the new variable is representing if it's somehow tied to the word cake or brownie.
Yeah, maybe it puts them in the situation and gives it more meaning to them.
I mean, that's how I would do it if I were doing the problem right now too, because I can lose track of like, what was X again? Is X K? You know, I'll forget it, and I'm not a middle schooler.
So it helps maybe with memory, right? It's a mnemonic strategy. Other ideas?
And it could be easily scaffolded to option B later on in high school. It could be like an initial kind of building block to understanding that other letters could be variables representing.
Great, yeah, great. How about, why did you pick X and Y? There was I think that had the most votes, so you must have had a reason.
This is generalizable, like you learn it in this context, but you also see X and Y in other contexts, so you can maybe, if you see it in other contexts, remember what you did when you learned about cakes and brownies.
Okay. They tend to use X and Y more in algebra when you're being taught algebra, and if you learn it that way initially, it might activate when you see X and Y again. Did anybody have a different reason? Yeah.
Also, if you have something like cake and cookies, that wouldn't really work in option.
Things that you want to represent might both have the same starting letter, right?
I feel like the X and Y make it more, drive home that it's a variable. That, you could set it at different prices. Like there's some problems where you could charge this much for cake and this much for brownie, or you could switch it if you want to make a certain amount of profit. And that the C and the B make it sound like it's one thing and that's it, at least in my mind.
Oh, that's interesting, because it relates to constants or something we use in math.
I mean, I know C and B can change too, but there's something that makes it much more concrete.
Yeah, it's interesting.
I was wondering if the symbols, like, at least in my head, it was like, could be even better just because they're not tied to, like, what they already, especially if they don't know the symbols, like, what they already know. So it's, like, less distracting. Because I feel like with letters, even X and Y, they could tie it to xylophone.
Yeah.
Yo-yo. Like,
so you're suggesting C and B might be more distracting because it ties to more things start with C and B?
but yeah, or even X and Y.
Mm-hmm.
Just having something totally.
Oh, so that's why you want this?
Yeah.
Mm-hmm. Okay. Okay, well, I think these views are reflected here. So mnemonic symbols link to the real world. They help students construct contextually relevant solutions, maybe. They're helpful, well, the fruit salad algebra approach where you can't, I'm sure you remember, like, you can't add apples and bananas. That sort of method may be helpful here. Non-mnemonic symbols like X and Y, though, may be better because children have prior experience with letters, right? Before they start learning to use letters to represent quantities, they use letters as labels, starting with Sesame Street. C is for cookie, right? C is for cookie. Cookie Monster sings that song, right? And, and as Susan alluded to, even in math, we use them as labels a lot of time. M is meter, right? And there are constants that are labeled with certain letters. Like, so we have an association between sort of letters as objects maybe, or letters as labels, and that might interfere with letters as quantities or letters as variables. So let me tell you about our study that we did to test this. This was an experiment with 322 middle school children. We took a famous problem from the math ed literature, Kuchiman, in 1978, gave this problem to children. Cakes cost C dollars each and brownies cost B dollars each. Suppose I buy 4 cakes and 3 brownies. What does 4C plus 3B stand for? So you can think about that and write it down. What do you think 4C plus 3B stands for? I won't make you share your results. It is true that undergraduates sometimes get this incorrect. If you feel very confident about your answer, maybe you might be willing to share what your correct answer is. What do you think is the best answer to that problem? I know math gives anxiety sometimes to people. Well,
how much money you would spend if you bought 4 cakes and 3 brownies?
okay, that's a wonderful, that's the highest level example, right? The amount of money you spent on 4 cakes and 3 brownies. What do you think, what's another correct answer that is a little less sophisticated? Total cost is still very sophisticated. See, University of Chicago students might not be able to come down a level. I understand that.
The cost of 4 cakes and 3 brownies.
Okay, here's what a middle school student who gets it right, but maybe not as sophisticated, might do. It stands for 4 times the cost of cakes plus 3 times the cost of brownies. That's still right, but you're not viewing it all as a structure itself, so it's a little bit less sophisticated. Now, what do you think is a common incorrect answer that kids might give?
The number of objects, 7.
It stands for 4 cakes and 3 brownies. or they might write 7 too. They view it as the objects, the label of the word, not the cost. Okay, so what we did in this study is we just randomly assigned children to get this problem. In Kuchiman's original study, he was in the Piagetian framework. He thought, oh, kids can't understand these kinds of problems until they're in formal operations. That's why be at least 11 or 12 before you can solve this correctly, or 14. I forget exactly what would that be, Susan? Formal operations. When does that start? I can't remember. Is it 14? Okay. What we did is we thought actually children's understanding of letters as labels, because his classic problem is posed in this way, might be contributing to the very poor performance that he observed. And so we just randomly assigned children to get that problem either with a C and a B in it, an X and a Y in it, or a phi and a psi. And then we saw how they performed. And here is how they performed. Let me talk you through this graph. This is the percentage of responses, so that's the percentage of kids. These are the people in the C and B condition. This is the X and Y condition. This is the phi and psi condition. Now, the total blue is correct. The total red is incorrect. The dark red is that worst answer that we don't like, that just says it stands for 3 cakes and 4 brownies, or 4 cakes and 3 brownies. I forget which way it is now. So this is that sort of letters as labels misconception. And the structural at the very top is that University of Chicago student high level understanding where they say it stands for the total cost of all the items you bought, or it stands for the total cost of 4 cakes and 3 brownies. And so what we can see here is that that's C and B condition led to fewer of the best answers and more of the misconception answers than the other 2 conditions. These 2 conditions were not significantly different from one another, though I will say there was a hint in the data. We worked with 6th, 7th, and 8th graders. 6th graders showed a trend that this was a little bit worse than this, and that's mainly because when they saw this, sometimes they just didn't answer it at all. So I think it was more likely that they would give up in this context because they had never seen something like that before. But the take-home point is that the performance was worst in the C and B condition, that mnemonic condition. Okay, so if you ask me, I would say maybe these 2 are going to promote understanding. It doesn't necessarily, this has nothing to do with learning yet, right? We haven't looked at learning. This is just performance. So that would be the next question. Does it matter for learning? We maybe have heard of the desirable difficulties effect. So is it the case that maybe things that are a little bit more difficult might actually help with learning? We don't know. This was only with performance and just sort of their interpretation of an algebraic expression.
Can I ask a question?
Yeah,
Do you
please.
think that this C and B, I mean, I was thinking, there's like this object bias, if the problem had to do with number of cakes equals C, number of brownies equals B, then
it might be helpful.
It might be helpful. So, for the mnemonic reasons that were mentioned, but because you have to ignore the number of objects and move to the price of those things, it leads to this,
Yes.
erroneous answer like Steve.
Yeah. So when you're using mnemonic things, I guess maybe a takeaway, or we could test it. It's like you want to make sure that you're using things that are exactly what you want the children to get. One reviewer on that paper said, well, what if you use C sub P and B sub P?
Yeah, like it's price.
Price, to indicate it's the price. So I guess.
Yeah.
Distracting. Too much confusion.
Too distracting.
Aren't the prices different? Or they could be different. Right. The prices are different. So that's okay. I mean, that's why you're the substitute. But I would do the opposite. P sub B. And
P sub, yeah.
Yeah.
Yes.
Then it's like you know that the
Right.
outcome will be a price.
Yes.
Right.
That's right.
Or you could not make it sub at all, just make it CP and B.
Sure.
Yeah. But sometimes when you have C and B together, that would be like multiplying those 2 variables.
Yeah.
It gets tricky. I mean, these little things that you don't think about, right? When you're... Okay, so that's sort of the last bit of evidence that I wanted to present to you. Just to summarize what I presented today, what I've tried to show you is just little pieces of evidence that even what we would think of as relatively minor differences in the format or structure of what we present to children actually affects their understanding, their performance, and sometimes their learning in mathematics. And I showed you that that a small change in the entities used for counting with children could affect their understanding of cardinality. I showed you that a pretty small change to the format in which we practice basic math facts affects their understanding of a foundational math concept, math equivalence. And finally, I showed you that a small change to the letters used to represent variables in an algebraic expression affected the way that the children interpreted that algebraic expression. And so I'll just close with a more general point and again come back to this idea that researchers in developmental psychology often study macro level differences in the environment and how they affect learning and performance. So things like family income, or they might focus on differences in the early childhood environment. And these things do matter. My point here is definitely not to say that these things don't matter. All I want to do is suggest that even smaller things that we don't always consider could potentially be snowballing in a way that leads to relatively large differences in the concepts that children develop as they grow and learn in the domain of mathematics. So it may be important for teachers and parents to pay attention to these sort of little things in children's environments, and even though they might not seem like they matter. So with that, I will end, and hopefully we'll have a good discussion. I want to thank all of these people who helped make this research possible. I want to thank Susan Golden Meadow and Susan Levine and Lindsay Richland and Christina. I haven't met with you yet today, but you're going to meet with me, and Darnell and Marjorie for taking time out of your schedules to meet with me during my visit today. And I want to thank all of you for your attention for my talk. So thank you, and I hope we can have a good discussion because I love getting questions. So.